Assalamu alaikum everyone. So in the previous session, as you saw that we were discussing the univariate analysis on the data. So the data set that we had was iris data set, in which we had four features. We had sepal length, sepal width, petal length, petal width, and the class. These are the features, and we had 150 data points in that. So we called these variables as independent variables or features, also called as features. Then we had a label, or we called it a dependent variable. So yesterday we saw how to make these scatter plots. So there we stopped at the histograms. I think I also explained you the histograms. So what was the necessity of seeing the histograms and things like that. Now today the question that I'll be taking, because out of these four features, now I want to see which of the feature is more important. Which of the feature is important? Is important. So if you see, now I have to define importance in some way. So how to define importance is basically if I have to use a subset of features in order to sort of get the label of a data point. So which of the features should I use so that I can do that? So for that, I'll do some analysis by using the histograms, and then we'll see which of the features is good, which of the features are having better priority or other features. So let's move to the coding window, and after the histograms that we started, we'll look back on the other graphs that we're seeing here. This was the histograms that we covered in the previous session. So now what I will do is I'll create what is called as a distribution plot. So basically that's just a smoothed out version of the histogram. So as if you see the histogram on the screen, so if I sort of connect all of these together and smoothen them out, because you saw that there are these steps. So if I want to smooth this graph out, so I'll get a graph out of these, and based on which I'll take some decisions. So the first thing that I'll take is I'll take each classes data like iris setosa, iris versicolor, and virginica, and for each of the features that I have sepal width, sepal length, petal width, and petal length. So I will plot the distribution, because this is the univariate analysis. Here you will use one feature at a time. So I'll plot the graph. Let me just comment whole of the code out. So I'll comment the code out till this part. Okay. So what I'll do is I'll plot this graph for all of the three species that we have, and we'll just use the sepal width histogram, and then we'll smooth that out. And here we have the function distribution plot, and the arguments that you see are sort of we have done this in pandas, so it will be easily understandable to you. Then we are using sky blue color, and the label and is this setosa, and there are some other arguments that you can look after. So we'll just print the first graph. If you see this here, the sepal width and density plots, if you see it on the screen. So here we get no idea basically. So if you want to separate out these things, so clearly nothing is visible. So because a sepal width is sort of intermingled with each other. So based on the sepal width, I cannot conclude anything. So for example, let's suppose we take this versicolor. So at 2.0 we have versicolor, but if you take this 3.0, we have the sepal length of 3.0 occurs in all the classes. So from this, it looks a whole mess. I cannot distribute. Ideally, what I want is, ideally, let me show you what I want basically. Ideally, the graph should look like somewhat like this. So it should be like this. Then I should have a space and something like this and something like this. So there should be a separation so that I can separate them easily. Let's suppose these are setosa flowers, and then these are versicolor, and these are virginica. Okay. So what I can write is, for example, if this value is 2 and this value, let's suppose, is 5. So if I can write an if else program for that. If let's suppose this is petal length. If petal length is less than 2, then it is setosa. Okay. Else else if petal length is less than 5, then let's suppose it's versicolor. And we'll write another else if it is less than suppose 8, less than 8 or something, or else it is directly virginica. So I want a separation like this, but you saw the feature that we have been analyzing. This feature of sepal width, it gives us no idea, because whole of the distributions, they're sort of on top of each other. So it gives us no idea about this. So let's try with the other feature. So we saw that sepal width feature is not that important for us. So let's try with other features if if we are able to make the distinction clear, so that we can at least get the idea which features are more important than others. So now the second plot that I'll be making is the plot of sepal. I'll be using the sepal length. So I'll just comment out this code and just plot the second graph now. So now you can see again the separation some sort of became a little bit clear. It is not as bad as the sepal width, but it is still the bad. For example, at 6, we have these versicolor and virginica quite overlapped onto each other. But still the separation is some sort of good. If I want to plot everything at once, then I have to plot two more things, because we have in total two features. So now you see that in the four graphs that we sort of plotted, petal width and petal length is are the two features that I think are much better than the other features. So you can see that in the petal width, this point after this point 5, we have a clear distinction of setosa flowers, and maybe there is a little bit of overlap between versicolor and virginica, but we found that petal width gives us some sort of stability, and it shows that petal width is a feature that we can use to separate the classes like setosa, versicolor, and virginica separately. If you see this petal length as well, I think the petal length is much better, because the separation between the setosa and non-setosa is more, and then you see there is less overlap than this petal width. So from these graphs, what we can conclude is that petal width is better than petal length is better than petal width, and it is better than sepal length, and which is much better than sepal width. So we can order these four features now. So we can order these four features. Let me show you. We'll order these four features. As you saw that this petal length, it separates out the graph quite well, and then it is better than petal width, which is much better than sepal length, which is much better than sepal width. So this is the order of features, order of features, like importance of order of features, how important the features are. We just plotted what I call as distribution plotted. They are basically the histograms, but we gave the smoothened out version of these things. So after doing that, we came to know that this petal length, this is the feature that we can use to at least conclude something like there is a lot of separation. If you again see those graphs, so here you can clearly see that these four graphs, like petal width, petal length, and these two graphs, sepal length and sepal width, they give us now the conclusion that this petal length is much better. If you see in here, so setosa, if I write a program now, if else program, I can say if petal length is less than 2, it is clearly setosa. I'll have no accuracy drop. I'll just with 100% accuracy say that all the setosa flowers can be sort of separated out by only using the petal length. Okay, so now if I am on this graph, so if you see the graph that's on the screen, the fourth graph, so I'll make maybe this graph. So what I'll do is the graphs look like this. So here we have setosa, they are clear separately. Then we have, let's suppose, virginica, and then we have versicolor like this. There is an overlap between these graphs. So here we have the two value. So what I'm saying is this is based on petal length. So based on this petal length, if I write an if else program, I can clearly see that setosa, I can sort of separate them without having an error. So I can write if petal length is less than 2, clearly it is setosa. So this will be 100% accurate. So I'll have no misclassification. So 100% accuracy will be in the setosas. But in here, if I, for example, choose a threshold values, let's suppose here the value from here to here, the value, let's suppose here we have 2.5 and here we have, let's suppose 3.5. So if I use this threshold, if I say that if the value is between 2 to 2.5, then these flowers are, let's suppose this is setosa, this is versicolor, and this is virginica. So if I set a range that between 2 to 2.5, the basically this range, this much. So if petal length is between these, I'll consider them as virginica. But you still see that some flowers are in this range. Some flowers are there which are in this range of greater than 2.5, and they are less than 2.5. There will be some misclassification error. If you see, there will be misclassification. So I can write else if petal length is less than, let's suppose, 2.5, and let's suppose then it's versicolor. But here I won't be 100% accurate. There will be some inaccuracy. So there will be inaccuracies. There you clearly saw, because there is an overlap in here. So again, in order to decrease that overlap, what I can do is I can take the threshold between these two classes as this point. This point can be taken as a threshold. Let's suppose this is 2.7. So now the misclassification I've decreased a bit, but still there will be misclassifications in there. But this petal length, this is the feature. That's the best I can do with this analysis. I can say that petal length is the feature which I can use which I can use among all the features if I want to classify them. At least I'll have some error, but it's better than other features. So as we saw this order, petal length is better than petal width. So we can use the combination of these two features then. But seeing this sepal width, we can only use this feature to conclude anything, because you saw that there was a whole overlap between these graphs, and we cannot conclude anything about this. Is the concept of these things clear? How do we saw the importance of all the features, and we saw the importance in the order of the features, which features are more important? Is it clear? Nice. Now you know that how to even choose the features if you have less features. There are other techniques. This is one of the techniques by which you can see these graphs and you can conclude which are the features are important. So as you saw these graphs, you saw these histograms. So in those histograms, what we had something like this. We had things like this, and then in between we had nothing. Then let's suppose like this, things like this. So if I want to smoothen it out, so I can, for example, connect all of these points together. So I can connect these points like this and like this. Okay, so this is what is called as PDF. It's called probability density function. So we'll have an in-depth study about these functions, what do they mean, but still here I would like to tell you about these functions because they'll be really important in order to analyze the data. So let's go into detail of the what is PDF basically. PDF, probability density functions. What it shows the likelihood. For example, what I mean by likelihood, so here if I take this point, this value, let's suppose this value is 6.5. So as you know, now know that there is a likelihood. So here if you go on the y-axis, so y-axis shows you the likelihood of points being there. So if you at random take a value and you see what is the likelihood that point will be there, okay, so by that likelihood you'll get to know that at 6.5 this much likelihood is there, the point will be, that point will have this length of 6.5. So informally I can say that it gives us basically the likelihood. It indicates the relative likelihood. Like if you have petal length, and if you choose petal length, and you may say if I at random take a flower and if it has 6.5 petal length, let's suppose this is 6.5, this is the probability, or this is the likelihood that the plant will be having the 6.5. So for example here you have very less probability. If you take a value like this, for example 9.5, so very less plants will have that. Let's suppose maybe zero point 0.2. Okay, zero point 0.2 if you take a plant at random and you are saying that what is the probability that that plant will have the sepal length or petal length of 9.5, it's zero point 0.2, it's very less. And if you take a flower out of this, let's suppose we have a flower 10.5, something like this, here the probability basically is 0. So you add, so it's impossible to find a flower because we saw that the length of these in our sample size was sort of between some value like between 2 to 8 and 9.5, something like that. So this PDF tells you the likelihood. If you take a flower at random, then what is the likelihood that the value will be in some range, or the value will be like this, like in the range of 6.5 to 6.7. Then that's why we have these buckets and bins. Okay, so that's what PDF indicates. Again, to reiterate it, PDF indicates the relative likelihood that a variable like petal length or some other has a specific value, showing the distribution. It should basically show us the distribution. Then we have what is called as CDF. This is PDF. Then we have what is called as CDF. CDF is called as cumulative distribution function. Just bear with me for a second. Probably you won't be able to understand everything fully, but when I show you the code example, then you will have a better understanding of these things. What cumulative distribution function shows that uh, if you sort of have these value, if you take a value of 6.5 in here, so what you are saying is how many flowers or how many percentage of flowers are having the value less than 6.5. Okay, so if I take the flower and a graph will be like this, let's suppose. So if I take value 6.5, okay, so this value will again range from 0 to 1.0. So if I take a value of 6.5, what I'm saying is at this 6.5, if the value is, let's suppose 0.8, or let's suppose 0.6. So I'm saying by this graph, by this cumulative distribution function, it says me that the flowers will the number of flowers which will have the value less than 6.5 for the petal length will be 60%. Okay, so it basically gives me the percentage of the flowers that will have a value less than a specific value. That's what this CDF gives me. These are not no means formal definitions. We'll go into formal definition. Well, we'll be reading about the probability and statistics, but here to just give an intuition about the things. What is this cumulative distribution function doing? What is this PDF doing? Probability density function doing? I'm showing you that. Let me show you a graph so that you'll be able to understand the things better. So if you see the things here, so what I have computed is, so if you see the code, I have the feature petal length. Okay, so I am taking the Setosa class and taking this feature petal length. So for this class Setosa, I am separating out that data. Now what I am doing is I am basically plotting the histogram that we had, and trying to like smoothen it out by using what's called as bin width and computing the PDF. This is the PDF. If you see this green curve, this is the PDF. Okay, so if I take the value between, let's suppose 1.4 and 1.5, so I'll just say the 1.4 1.5 means like you will find 0.2% of the 0.2% of the plants which will be having, like, let's suppose the value of say 1.4, or maybe 0.27 percentage of flowers out of 100%. So area under this curve will be sort of 1, it will be equal to 1, because area under this curve basically gives us all the flowers that follow this distribution. Again, to show you the graph and explain you some bits of this graph again. So this graph looks like this. So we have a PDF, and then we have a CDF which we have colored in red. Let's have that in yellow, and we have a PDF like this. Okay, so this is our PDF and this is our CDF. So what PDF does is it shows us if in a specific interval, let's suppose we take an interval like this much, it shows how much percentage, or the probability or the likelihood of, let's suppose we are having the petal length for Setosa flowers. So we are basically giving we are plotting the distributions. So let's suppose this value was 1.4, 1.4 to 1.5. So in this ninja 1.4 to 1.5, how much percentage of the flowers are there, or what's the probability that we'll find the flowers here in here? And you saw that the probability here was given as 0.4 or something like this. So this was 0.4. So the value 1.4 to 1.5, zero point 0.4 will have the probability of 0.4 of finding the flower there. So this is the PDF. What CDF means that if I take this 1.4 now, so 1.4 is like till here. So if I have this, so let's suppose we get the value of 0.6 here. So what it shows you, it shows me that 0.6 or 60% of the flowers have the petal length of less than 1.4 in the Setosa category. In the Setosa. Okay, is the concept of PDF and CDF to some extent clear, like intuitively, because we'll go into formal definitions again. I promise you that we'll see the formal definitions. But have you seen what are they used for? How to? These basically are called distribution plots. Distribution plots. So if there is a question, maybe I'll stop here because I know that these concepts may be new for you if you haven't studied probability. So if anybody has a question, so he can ask me right now here, because we'll be doing the analysis based on this CDF and PDF. Okay, I think there are no questions, and I'm not able to see your screen because I have the code window on the next side, so you can just speak out the things if you understand and if you're not understanding. Anyone among you? Okay, that's the concept of CDF and
सर
PDF.
थोड़ा सा ये PDF CDF थोड़ा सा रिपीट कीजिए.
Okay, sure. So what I'm saying is, if you have the data, you have this data, and you plotted the histogram. If you understood the concept of histogram, and then we smoothen out the histogram and we get PDF out of that. So what PDF does is, so area under this curve is 1. Area under this curve is 1. I'll tell you what area under curve means because we have to go into the calculus part of that. So right now what I'm saying you, if this is these are the two curves. This is called as PDF, this is CDF. If you see it again on the screen, on the coding screen which I wanted to show you. So here have a serious look on this. there is a function in the red which is CDF, and there is a function which I have computed. It is in the green, which is a PDF. Just have this graph in your mind, and again I have plotted a similar graph on the screen to explain for you. So if you see that graph, this is like this. So what this PDF now indicates, just keep that in mind and have the graph in the mind, and I'll explain you what this PDF means first. So you had that histogram. If you saw the histogram in here which I plotted a while ago, so you smoothened out it. So what was the meaning of this? So if you watch the cricket match, so there you also have, let's suppose, overs were here, and then you have runs conceded. Okay, the runs conceded and the overs that we had. Let's suppose in the first over we had some 5 runs, so we'll make a graph of 5. And let's suppose in the second over we had some 8 runs. Okay, then in the next over there were only 3 runs. Okay, and let's suppose for a lot of overs we have data like this, some data like this. The data was like this. If we smoothen out this histogram, let's suppose it's like this, and we'll just connect these points together. So we'll connect it like this. Okay, so this is what I call a PDF, because you saw that overs actually are a continuous range. They basically are discretized, but here we have 6 balls, and after 6 balls we compute that, and these values are sort of what I can say is continuous in the continuous range. Okay, so this is what I call as a PDF, smoothed out version of histogram, like informally speaking. Then if I want to find the score, for example, if I take a point over here, so let's suppose we are taking a point over, let's suppose it's a fifth over or something like that, and you can clearly see how many overs were conceded in that over, in that fifth over, how many runs were conceded. So you can just see this. Let's suppose that 12 runs were conceded or something like that. So similarly in the PDF, in here we had this PDF. So this data distribution was for the plants that we had, and we had taken a special only one species, that is Setosa, and we are analyzing its petal length. Okay, petal length is the thing that we are analyzing, and these are the points that we got. This is the smoothened out histogram that we got, and smooth, we call it a PDF. So now we have the range of values that you saw. We have the range of values out of which we got this histogram. So this range was from 1.0 to 1.8. It was, the graph was like this. It was like this. So we had the values till 1.8. So what I'm saying if I pick the Setosa flower at random, if I let's suppose I have a bucket of Setosa flowers. So here there's a bucket of only Setosa flowers, and if I measure its petal length, okay. So let's suppose here we have this 1.4 value is here. Let's suppose 1.4 value is here. So I'm saying if I pick a flower of Setosa at random out of a bucket, and if I measure, what would be the probability that this flower will have the petal length of 1.4? So you can get that by here. So here we have this value of zero point 0.4. Zero point 0.4 basically means that there's a 40% chance. There's a 40% chance because from the distribution that we saw, whole of these plants they belong here. But you saw the peak is over here. If the peak is over here, that the probability of the flower, the Setosa flower having the petal length of 1.5 is nearly zero point 0.4. That's what I mean by this PDF. As you saw that we computed this PDF from the histograms and we smoothened out it. Then what is this CDF basically is, if you now take this 1.4, in CDF you're asking a different question. In CDF you're asking a question, the difference in the question. In PDF you're asking a question is, what is the probability, or likelihood of the value. Let's suppose there is a value of the value. If you take this value petal, here we have this petal length as the value. What's the probability of the petal length or a particular value if we selected Setosa, if we selected Setosa flower? So this is the question we're asking. We basically are asking, if I take a flower at random and I want to see the specific value, so what's the probability of that specific value for that plant? This is the question we ask in PDF. Okay, I hope that you got the question. In CDF, the question is, if I take a value, let's suppose here we take a 1.4 value, how many number of, let's suppose, how many number of, in our particular exam we have these flowers, how many number of flowers, or the percentage, basically we take not just the number, we take the percentage or probabilities, how many number or how many percentage of flowers have value less than equal to, let's suppose in here 1.4, or a particular value can be there. So these are two different questions. In PDF we ask the question, if we take a flower at random, what's the probability that we'll find the flowers petal length as 1.4. In the CDF, we're asking a question. So how many flowers have the length less than or equal to 1.4? This PDF shows you how many flowers or how many percentage of flowers have the length petal length as less than or equal to 1.4, and this PDF says you what is the probability of the flower that is having 1.4 petal length. So is the distinction between PDF and CDF clear?
Yes, sir.
Okay. This is the rough sort of intuition, but we'll go to the random variables in the probability, and then you will sort of see what is the meaning of that. And if you need to watch these lectures again, there is no problem in watching them again, because sometimes when you hear the new terms, and that time you may feel that I have not understood it fully, but after watching 2 3 times, and you will get the concepts really clear. So again, I have plotted these CDFs and PDFs here to get the distribution of the data. Okay, that's what I have showed you on the previous screen. Okay, so here that is, I'll just switch the screen to again show you that. So here is that. So here if I take this 1.4 value, so this the below green line is actually the PDF. It says me that if I take a flower setosa at random, what is the probability of getting that? What percentage of flowers will have that? So here I can say that it is nearly like 0.3. Like there is a probability of 0.3 that the flower that I'll take at random from the setosa flower, it will have petal length of 1.4. But in the PDF, in the CDF, what it does is it tells me that how much percentage the flower. So here we have zero point 0.6. That's why it ranges from 0.0 to 1.0. Because I know that each of the flower will have the maximum petal length is, let's suppose, 1.9. So you saw that at 1.8 we got the 100% probability. Like if a flower if I take a flower at random, so what's the probability that I'll get the petal length as 1.9? So 100% flowers will will be having the value less than or equal to 1.9 for the petal length. So for this 1.8, there are very less flowers which will have this length. So that's what these PDFs and CDFs mean. Okay, we can compute these PDFs and CDFs by using some other things. For example, I have used KD plots, I think, if they are there. Here we have these plots. We have directly used the functions of eCDF, and we have created the PDFs as well. This is the PDF. This is PDF that we have used by the functions, and this is the CDF. Like this is not in a smoothed out version. If you see it on the screen, this is not a smoothed out version. So we can smooth it out to get the CDF out of it. So by using the simple libraries, what I did is I created a histogram, and out of that histogram, I create the PDF. If you see it, so when we'll go into the formulation of how this PDF is computed, so that time you will have the sense of why I have divided these counts by sum of counts. Then there is only one line of the code which I have written to compute the CDF. That will get clear, I think, in next 5 to 6 minutes. And why I have done it, and I got these PDF and CDF. Is it clear now? So can I move ahead?
Yes, sir.
Okay, nice. So again, having some discussion, why do we need them, and why do we need these PDF and CDF? The first thing is you can get to know the distribution. You can get to know your distribution. The first thing is why these distribution, why we plot these PDF and CDF. So the first thing that I'll write is get to know about the distribution of the data. Distribution of the data. As you saw that we have in that curve of PDF, you clearly saw that there is a high probability that we'll find 1.4 1.4 value of petal length for the setosas. So that's why we got to know the distribution of the things. Okay, then again we saw if the data is unimodal or multimodal. So you know what is unimodal, and then there is some multimodal data. Multimodal. So unimodal, this is basically called as mode. The peak basically is called mode. Informally we call it a mode. So I don't want to get into formal mathematics again, it will be boring. So we'll deal that separately, what is a mode, what is unimodal. But here I want to show if the data looks like this, or maybe data looks like, for example, execute version also like this. So you saw that only there is one mode. So but if data looks like this, the distribution of data basically, so you saw that here we have these multiple mode. This is called as multimodal data. So this is tricky to understand, this multimodal, how to handle this data. But if you somehow got this unimodal data, so it will be easy for us to sort of grasp and deal with this data. So we get to know about these things by using this PDF analysis. The first thing is we'll get to know the peak, the distribution, and we get to know if the distribution is like unimodal, and in the clearly we saw that we have only one mode in the data. The data is not haphazardly separated, haphazardly distributed. So there is a particular pattern in the data that we saw. In the CDF analysis, what it indicates that, as I told you that in this CDF, it basically, why is it called cumulative? So how does we compute this CDF is, we actually can compute it from PDF. So if you have PDF, so now you have these many flowers are having this 1.1, and then we have, let's suppose 1.2 over here we have, let me just erase this to show you clearly. Okay, so these are the values of 1.2, then we have this 1.3. If we sum these things up, for example, here we have some value, here we have some value, then here we have some value. For the next point, let's suppose for this 1.4 over here, you'll sum up these things. So you'll sum up this and this, and then that will be the value for that. That will be the value for this 1.4. Again, let's make it separately to understand it better. So you have a PDF like this, then you saw that your CDF looks something like this. So what I'm saying is, if you have a value and you have, for example, 1.0, then you have, let's suppose, 1.1, then here you have 1.2. If you want to compute, so you basically just take the summation of these things to compute the value over here. That's why this graph is always increasing. If you see, it's increasing graph, it's never decreasing. It's not like this, it's not a haphazard graph like this. Why? Because we just compute this CDF from the PDF. How? We just compute the sum of these things together. So you saw that if I'm asked, if I take the petal length and it is 1.2, what's the probability, and I'll get the value over here. So the question in the CDF is that how many setosa flowers will have the petal length less than or equal to 1.4. So I'll say they can have the flower can have length of 1.0, they can have the flower of 1.1, and everything that is below this. So that means basically I have to sum up these things, I have to sum up these probabilities. So is the concept clear? Why do we sum up these things? Because in the PDF we ask the question, what's the probability of having the petal length of the value of 1.2 for the setosa, and this is the value. So in the CDF, the question basically is, how many plants or how many setosa plants have the value of petal length as less than or equal to 1.2. So less than 1.2 basically means 1.0, 1.1, and 1.2 itself. So I can just sum these things up. So these many number of things are there which I'll get CDF out of that. So if you know a little bit of calculus, so if you integrate this PDF, if you integrate PDF, you will get CDF. Or if you differentiate, I'll say differentiate this CDF, you will get PDF. That's why it's called cumulative sum, cumulative distribute, because this is called cumulative sum. So if you have an array like this, if you have an array like this, 1, 2, 3, 8, 9, 10. So if you make an array where you sum up previous elements, let's suppose we'll put 1 in here, then we'll sum up these two things. 1 plus 2 is 3. Then we'll sum up these three things. 3 plus 2 plus 1 is 6. Then we'll sum up 8. 8 plus 6, 14. Then we'll have 9, for this is 23, and so on. Okay. So now this is an array. If this is an array, so this we call as cumulative sum array, because we have done this cumulative sum. We have added the previous elements. So in the similar fashion, in the PDF, if you just sum up the previous values, you get the CDF out of that. But now these values are so small because this is a range of continuous values. That's why we cannot perform summation. If you know a little bit calculus, you know that now we have to perform integration. Like this is some sort of like bad to use that infinite summation is integration, but still for the sake of understanding, as we have to infinitely sum the smaller elements because these are infinitesimally smaller, so we'll have to integrate the things. Okay, so from that you will get the CDF. Okay, that's how I wanted you to feel the connection between the CDF and the PDF. And I was discussing the things like what you can do. You can get to know about the distribution of the data, whether where is the peak, if it is unimodal, and in the CDF you can easily get to know, okay, how much percentage of the flowers are having the value less than equal to this. So why is it important? Let's suppose I am working, let's suppose, in Amazon. So I have this customer data. Let's suppose delivery days taken to deliver a product, to give a real world example why they are used, so that it motivates you to learn enough of these. So let's suppose I have the data of days taken to deliver that product, days taken for the shipment. Okay, so I can have a lot of days. For example, I can for some customer it will take just 1 day, for some customers it will take 2 days, again 1 day, then I have like 4 or 5 days, and let's suppose maximum we can take 8 days for some people, and there will be a lot of values like this. If I plot these values, it will like look like this. For some people, the one day taken for the people, let's suppose they are 200 people, and for some other people maybe distribution will look like this. I'm just plotting the histogram first. Okay, it will be something like, if I smoothen it out, if I smoothen this graph out, so this graph will look like this. Let's suppose this graph will look like this. Let Now you saw that at this value, for this is 1 day, 2 day, 3 day, 4 days, you saw that most the people they get their order at 4 days. So I'm saying, so how much people get their order? So most the people, let's suppose these are some 500 people which got the orders on the in the within the 4 days. Okay, so from this is a PDF. From this PDF I got to know at random, if I deliver the order, if I deliver the order to the people, so at random there is, let's suppose if we have some 10k people, out of them we have given 5, let's suppose the probability is say zero point 0.4. So zero point 0.4 chances are there I'll deliver the product within the 4 days. That's the question that PDF will answer. So what will CDF answer is, so if I create the CDF of this, CDF will look like, so look something like this. It looks something like this. So I'll sum up all these 200 people plus, let's suppose here we have 300 people, here we have some 400 people, we have 500 people. So I'll say out of all of these people, if I sum them up and I say that nearly, suppose 1000 people out of 10,000 people will get order within the 4 days. Okay, so how many people are there who are getting the shipment delivered within the 4 days? We'll sum up the people who got the orders within the first day, within second day, and within third day, and within the fourth day. We'll sum these things up. Okay, and we'll get the idea. And if you want, if you might have seen that Amazon gives you the expected rate of delivery. They see the location that you are in, and they see the previous data when we delivered the shipment, how much time did it take, and they, let's sort of keep the safe hand, they'll say 8, because they have seen that they might saw that 95% of the times we get the order delivered in your area within 8 days. That's why they'll say will take 8 days to deliver the order. And then you might have seen in the Flipkart, Amazon, they deliver the products beforehand most of the times, because they are taking this upper cap. They are saying 95% of people within your area they got the delivery within the 8 days, so it is better for us to give you the expected delivery as 8 days. Okay, is the concept of PDF CDF intuitively clear? We'll go into the mathematical details in depth, but I want you to know the intuition behind these things. Why are they necessary in analyzing the data? Is this clear?
Yes, sir.
Yes, sir.
Nice. Now what I'll show you, I'll again go back to the coding window and show you some other graphs comparisons basically. So in here what I'm doing is I'm comparing these things. I'm comparing PDF and CDF of each of the petal length, each for the Setosa, Versicolor, Virginica, we have PDF and CDF over here. If you see this graph, so this again we have a KDE plot that is there in Seaborn. You can easily look at this code how to plot these graphs. So it's not difficult. So it'll be easy. That's why we have went through that matplotlib and how to use those. So here we have these graphs. The first is for the Setosa. This is the Setosa PDF, and then we have the Setosa CDF. And in the similar fashion, we have this versicolors PDF and versicolor CDF. Then we have Virginica. And clearly, if you see here, this is well separated. This graph is well separated. What is that? What do we get out of this? As I gave you the Amazon example, so it is pretty clear from that. So here, if there is an intersection in these graphs, so you can clearly say that value of petal length is less than 2. I can use the tablet to show you it better. And we had the graphs like this. So this was our PDF, let's suppose, and we had the CDF like this, something like this. It will be a continuous graph. Then again for the other graph we had things like this, and then we had like this. It should not be infinitely increasing. It should be like tapering off. Okay, tomorrow I'll make sure that I'll write on the graphs. Then we had to make other graphs like this is the PDF and this is the CDF that we have, let's suppose. Okay, so this is the CDF. So if I want to take informed decisions again, what this PDF will help me in here. So I'm pretty sure that here we had this 2, and if petal length is less than 2, we have the Setosa. So 100% accuracy in here. Now I want to see how much inaccuracy will be there. So if I sort of have the threshold in here, so I'll use this point as a threshold. Let's suppose we have the threshold of this is 4. So I'll say if the petal length is less than 4, this is our Setosa, and this is our versicolor. This is our Virginica's graphs. Virginica. Okay. So if I take this threshold, Okay, if I take this threshold as 4 and I'm saying this is a versicolor, so I want to see how much percent of error will be there. So what that will be computing by using this CDF. So I'll just say, because till here let's suppose 95% of the flowers will be virginica if I have the threshold 4, but still there is some percentage of flowers. If you see this much a graph, like zero point 0.5 of the graph, so there we'll have the inaccuracy. So we are sure that we'll get 95% accuracy in here. So by computing this PDF and CDF, and if I put a threshold over here, I know that for 95% of times I'll be accurate if I set this threshold as 4, and for the other 5 percentage 5% points I'll be wrong. So in here again, so how much will I be wrong for the other things? Let's suppose this is the CDF and the value of the CDF over here, let's suppose is zero point 0.2. So in the Virginica side, I'll have 80% accuracy because 0.2% I'll misclassify them, because you saw here we have this Virginica's CDF. So this portion will be wrong for the Virginica if you see it. So this is the example how do we analyze these graphs, and if I have to set the threshold, if I just write some if else programs to sort of distinguish, because do not forget the goal. The goal here is that we want to classify the flowers. That's the goal. So I'm sort of trying to make an if else program. If it works with if else, then I don't need to make it complex model like that. So here I saw if I have a threshold of 4 only by using this petal length, so I'll get an inaccuracy of 95% for this versicolor and maybe 20% for this virginica. So that's by using this CDF and PDF. If you understood this, I think it will be easy for you to. If you have understood CDF and PDF, it would have been easy for you to understand the example that is on the screen right now. So how many of you have understood this point? I also give the Amazon's example. Okay, so that's the necessity. That's the thing how we use these PDFs and CDFs in the real world. I think Amazon daily uses it in the e-commerce websites, and how to deliver the products. What recommendations show YouTube uses that, because they have to see the distribution of the data. I hope that this is clear, and I can move ahead with the other examples. Now I'll this discussion was sort of involving for you. Let me give you a break of maybe 1 minute so that you take a breath, because now the easy concepts are again coming. I don't want you to feel that it is tough. How many of you felt that this discussion was sort of involving? कितने लोगों को लगा कि बहुत involve होना पड़ा इस discussion में? Okay. So nice. Now the easy things are again coming. So my job here is to make the content as easy as possible for you guys. But here that's why I gave a brief introduction of PDF, CDF to you, and this is intuitive idea. When I'll be going the mathematical details, now you know the intuition behind that. Now it will be easy for me to explain it mathematically, and you will have the more grasp that time. Okay. Now we'll again go to some statistical properties. Statistical properties. And this again is, this won't take a toll on your brain, it will be sort of easy for you. Okay, let's start with that. Let's start with the mean. I'll explain you the mean first, then we'll see what is the necessity of mean and things like that. So the mean, basically, sometimes there are a lot of types of mean. There are types. One is called as arithmetic mean, one is called geometric mean, then we have something called as harmonic mean. One specifically I'll be talking about here is arithmetic mean. This geometric, okay, sorry. So what I'm saying is we'll be now discussing the statistical properties about the data. The first thing that I'll be talking about is mean. So there are three types of mean. One is called as arithmetic mean, and this is called a geometric mean, and the last type is called harmonic mean. So here we'll be focusing on this arithmetic mean. So we'll be also reading about geometric mean and the harmonic mean where we'll be using them. And here I want to explain you the arithmetic mean first, then the necessity of what it explains and what it shows and what can we learn from this arithmetic mean about the data. So basically what mean means, if we have, let's suppose, some samples. Okay, yesterday I explained you the difference between sample and the population. Let's suppose I have a data set X, and in that I have data points X1, X2, X3, and so on till, let's suppose, X10. So what's the definition of arithmetic mean is, I'll sum these things up. Summation of Xi's. I is equal to 1 to n and divided by total number of observations. How many are there? So it was 1 to 10 divided by 10. This is what I call as arithmetic mean. This is the arithmetic mean. So if I write in English, so in English I'll say sum of the elements and divide it by the total number of elements. So it is sum of all values divided by total number of values. That's what I wrote mathematically over here. This symbol, if you haven't seen it, this is the summation symbol. Okay, this is the symbol of summation. Okay, we go from 1 to 10 and we add all the values that we have and divide by 10. Okay, this is the basically the formula of the arithmetic mean. Okay, this n, or if I write it in general terms, so if I say average is basically denoted by this symbol mu. Okay, so we'll write mu is equal to summation of, let's suppose xi is ith data point, so I goes from 1 to n, let's suppose, and divide by n. So n here is number of data points. So xi here is value of ith data point, and this is the summation, and here we have this mean. This is called as arithmetic mean. I hope that you understood this. This is a simple concept, but I had to made clear two things in here. Why did I wrote it like this? The first thing is mathematics is a language. Mathematics is a language. That's the reason I showed you this example. Now you can read this. So this is how you can read this. You can write sum of all elements divided by the number of elements is equal to the mean. So I read this basically in English. Sum of all the elements divided by the total number of elements gives me the mean. So you saw that it's like poetry. The whole of the 2-3 lines I just captured that in one formula. So that's the first thing. Mathematics is a language, and you must know how to understand this language. When I write some equation, you should be able to sort of write that in English. You might have seen many mathematical equations. Why do people feel bored about these mathematical equations? The thing is, they do not know how to read these equations most of the times. So the best thing is that you read these equations in plain English. That's the thing here. If I had to divide mean is basically summation of all the data points divided by the number of data points, and you get the mean out of it. That's why I wrote these things in this format. And now we'll see what this mean basically indicates. Why is why is it important? It shows us the central tendency. It mean shows us the central tendency. That's why we usually talk what's the average age. So average age of the people, usually you might have seen 75 years. That means like central tendency, that most the people in the distribution they follow the 75 at average. And if you see at average how much time do you spend in learning the new things, you might say 2 hours a day. So that's an average. Maybe sometimes you do not spend any time, sometimes you spend 6 hours or so. But I want to know about the central tendency, like what's at average, what do you do? Okay, that's the meaning of this mean. And then other thing is, we can do by using this mean, we can perform comparisons. So what I mean by that is, now you know that there is some tendency of the value having this. Now you can compare the different groups by using the mean. Let's suppose we have petal length, petal width, and sepal length and sepal width. So in this example, you can just say the mean value is this, the mean value is this, and you can say the higher. If there is a higher mean, then the values usually are higher. Let's suppose in a real world example, if I take the example of Rian and I take the example of, let's suppose, Mavish, or things like that. And let's suppose Rian's average income is $12 a day, and Mahavish's average income is $15 a day. So what does it indicate? It does not indicate that every day that Rian earns like $12. It says that the tendency is 12. But at average, we can say if Mahavish has the higher average, then she's richer than Rian. So basically, we performed comparisons based on that. Okay, so that's the significance of this. The first significance, it shows the central tendency. Then based on that, we can perform the what is called as comparison between these things. Let me show how to compute these things, and we'll compute the mean of petal length maybe for all the classes, and we'll see. Going back to the coding window to show you that. Here we have again, we chose this petal length for all the 3 classes that we have, and we want to see if we have petal length, which of the class has higher petal length. We want to see the average of these things. So if I just run this cell, I hope that it will be easy for you to understand. It is mean, actually this is the mean. So here we have a function mean. So you can use the numpy as well. I have used pandas. You can convert them into numpy arrays. Then there is a function np.mean. But the panda data frame also provides us with a function of mean, so you can also calculate it. You saw that mean length of setosa petal length is 1.4. Mean length of versicolor is 4.6. Mean petal length of virginica is 5.52. Now you clearly know that the setosa flowers are smaller than versicolor and virginica, and virginica is bigger than all the flowers. So now if you see the flowers, and if it is a smaller flower, high chances are that it is setosa flower. So we computed the mean, and we got to know that smaller flowers are usually setosa flowers. It's not the case, but high probability is there. That's why 1.4 is very smaller than other. If you got the biggest flower, there's a high probability that it's virginica type. Okay, based on the petal length that we have. That's how we use mean. Okay, is the concept of mean clear?
Yes, sir.
Nice. Now, there are problems with the mean that I'll also tell you. So the first problem with the mean is that it is sensitive to outliers. It is sensitive towards outliers. So what is the meaning of this sensitive towards outliers? So as I yesterday showed you that if something is out of the norm, that's an outlier. Let's suppose we had this 2, 3, 4, 1, 2, something like this. These values are normal, and if the average value here is, let's suppose, 14 or something, not in 14, it can be like 3.2 is the average value. If there is a value which is, let's suppose, 100, and now the mean got shifted, it is no more 3.4, it will be much higher. Let's suppose it will be 30 plus. So now by just adding one value, which was sort of an outlier, which was not like the all other normal points, we got the central tendency shifted. The central tendency was shifted. Now we cannot say the average age is this. In the people, you saw that we say that average age is 75, but there can be a person who lives for 200 years. This person is an outlier. An outlier, they basically impact the mean. So if I want to show you it in the code, let me show you it in the code so you understand better. I want to basically add the thing. So what I can do is, so here I have this mean petal, and I'll just do one thing, write in the code and see how I will change the code. So I'll write this mean petal and setosa. So I'll use the numpy array. I'll use make it numpy array because there is a function as well. Import numpy as np. So what I'll do is I'll just use np dot mean, so I can compute the mean of this. Okay, so I can comment out this line. So this is the other way. So here I wanted to show you the other way, mean petal length of setosa. So if I run this cell, again the values are similar. But why I did this, why I computed it with the numpy, because here I can append the values. So I'll just say np dot append. So what I'll append to this value one more value. Let's suppose 200. So basically I'm appending one more value which has a petal length of 200, and now I want compute the mean. So here this is the normal mean that we have. Let's suppose I'll call it 1 here. So this is the mean that we have, and then we have this setosa with the outlier. So here we have this one. So now you will see the impact the outlier puts on the mean. So original mean was basically 1.4. Now you will see what's the, now you saw 5.35. I just added one wrong value. I just added 200. Whole mean tendency got shifted. We got the value of 5.35 now. Initially it was 1.46. So outliers had a huge impact. If I add some other value, for example, let's add some other outlier 500. Now you will see the problem. Sorry, I have to append this value. I have to again make a list of these, but I don't want to make a list. So let's suppose I just added this, and you saw that the mean with the outlier got shifted to 5.3. Now you saw that the mean is sensitive to outliers. So if there is just one outlier, whole of the mean got shifted, and we cannot say the central tendency is this. That's why we have to deal with the outliers. In the yesterday's session, we also saw why do we need real outlier, and that you saw that this mean is impacted by the outlier. Is the concept of outliers and how does it impact mean clear?
Yes, sir.
Nice. So after that, I'll go with the concept of variance. Okay, I'll go with the concept of variance. So just remember that mean gives us the central tendency. Now I'll go on the concept of variance. What variance basically means. What it does, variance, it also it quantifies the degree of spread. Quantifies the degree of spread. What I mean by that is, so now you know the central tendency of the data is, let's suppose, 4. So we have, this is the central data and central tendency. But you know that the value can range from, let's suppose, 1.4 to 8, somewhere around here. So and distribution is like this. It is like this. So this is what I call as spread. This is the spread. This is spread. The dispersion, basically, how much the spread is in there, how much data is dispersed. So the range of the values, basically, it gives you. That's why I have written, it quantifies the degree of spread in the set of values around the mean. It shows it is basically, it shows how much does the data point vary, how much the other values vary around the mean. So this is around the mean. We have the mean value, let's suppose 4, and it starts with 1.4 and 8. So it will be, if I compute the standard deviation, it will be the variance, it will be 4. Because if you some sort of 3, let's suppose 3, because 4 minus 1 is nearly 3, and 4 plus 3 is nearly 7. So there is a spread of the data. So if I compute the deviation here, this variance here, it will be the value 3. Because if you add 3 values here, you will get to 8. If you minus 3 values here, you will get to nearly this 1 value. Okay, if you subtract these 3 here, you will get to 1, and if you add the 3, so it is 4 plus minus the variance. So it will basically give you the spread. This is mean, and this is plus minus variance. So what is the basically mathematical formulation of that? If let's suppose now we have these n values. So now you will compute the mean. You have the mean that you computed, which I'll denote by mu. You have that mean computed with the data. Okay, you know how to compute the mean. Now you will subtract each of the values. So we have an x data set. We have x1 point, x2, x3 till xn. These are the data points. The first thing we'll compute is mean. The mean will be summation of xi's. I goes from 1 to n divided by the total number of data points n. So this will be the mean. Now how I will compute these things? Look here. So I'll take each of the data point, this x1, x2, x3, and subtract the mean from that. So I'll say x1 minus mu. I'll do that. Whole square. Then I'll say plus x2 minus mu whole square plus, and so on till xn minus mu whole square, and divide it by n now. This is called as variance. It is represented by sigma. This is a symbol. This is variance. So I'm saying the how much is the first point far from this mu, how much is the second point far from this mu, how much is the nth point from this mu. And why am I squaring it? Because sometimes the points can have negative deviations. As you saw that mean can be right here, mean can be here. So point can lie here, point can lie here. So if you just compute the, if you just subtract this mu from here x, and you will get a negative value out of here, you will get positive. But in order to smoothen out, in order to get the general overview of how much deviation, how much dispersion, we square these, because you know that any number squared by any number, if it is negative or positive, if it is squared, we get a positive number always. So in order to get that positive number, in order to just negate that negative values, what we do is we'll take a square of these things. So again, reading it in English. So we computed the mean. I told you that what variance shows is it quantifies the degree of spread. Now I want to show, now I have mean, how much each data points varies from the mean. So I can say x1 minus mu. This basically gives me how much this data point x1 is far away from the mean. For this x2, I'm saying how much is this x2 far away from the mean. I'm computing it for all the points, then dividing it by the number of points. It gives me at average. This basically again is an average. So this is average of these the points are how much far are they from the mean. So if I write in succinct way, so the sigma basically is equal to, what I can write is xi minus mu whole square summation I goes from 1 to n divided by the n. This is what is called as variance. Okay, this is the formula of variance. So this again gives me the spread of data, spread, how much data is spread across, spread or dispersion. Again, if I want to sort of again write it in expanded version, so I can expand this mu as well. So I'll say I is equal to 1 to n xi minus, how to compute this mu is again summation of I is equal, let's suppose j is equal 1 to n. Now I'll say again xi. Now I'll write whole square, and here it has its own n. Now there is an n over here as well. This is actually small, and we'll put small n on the both sides. So are these mathematical equations? They might look scary, but if you understood them, they are really easy. They are not that difficult. So how many of you feel that this is not that difficult? These reading these equations is not difficult. If I'm nice. That's why I want you to introduce the concept in such a way so that you feel that we can read these equations. This math sometimes looks scary when you see it on the books or see it on the research papers. It might look scary, but they are really simple things, and they are basically something somebody has to write something in plain English, but it takes a lot of space. So in order to save the space, we write the things in mathematics, and it's easy to manipulate these things as well. Then, so this is what I mean by variance. So again, why to use this variance? Because I want to get the distribution, how my data is spread. Okay, let me give you the significance. Let's suppose I'll write significance of this. Significance. The first significance is I measure the spread. Measure the spread. That's why we are quantifying everything that we like. Again, I'm derailing from the topic, main topic. So here, mathematics. Why do we use mathematics? Because we have to communicate our ideas to the people. So in order to communicate it better, in order to quantify the things, we must use some mathematical tools. So अगर मुझे कोई भी problem formulate करनी है, so I'll formulate the problem. Then in order to make the machines understand that, I'll have a mathematical formulation. I'll quantify the problem basically. If I'm unable to quantify a problem, then I cannot basically solve the problem itself. So that's why I told you I want to see the spread of data. Then we came up with the measure of variance. So variance basically is a tool by which I can show you how my data is spread across. Okay, so this is the significance of using the variance. It measures the spread of the data, how much spread is there. So if somebody says you that deviation is 0.5, and he must also give you the mean. This sigma is variance is 0.5, and if the mean is 1, so you can say that generally the data will lie on this zero point 0.5. 1 minus zero point 0.5 is 0.5 to 1.5 range. So this will be the spread of data. Maybe data will look something like this. So you can just have an overview that the least value will be, I think, around 0.5, and the highest value will be 1.5. And the tendency is 1. So this is the spread data that we'll be having. By just knowing this variance, you can know the spread of the data. Because there is a component of mean. As you have this mean over there, as you have this mu in the equation, so again this is impacted by the outliers. So again, if you have an outlier, the variance, the spread will be impacted by that. To show you how to compute the spread, to compute the variance, let's go to the coding window and show you that. So here we have, I think it's here. So here we have a function variance var in the pandas data frame. We can apply it directly to compute the variance. So you saw that 0.3, 0.03, 0.2, 0.3. What can you conclude from this? Because I told you whenever you're performing something, make sure that you observe the data and you conclude the results out of it. You saw there is very less variance in Setosa. There is very less variance. There is very less spread. The values are not that spread. There are not much unique values. There is 0.03 spread, very less spread. And then in the versicolor, there is a little bit spread, zero point 0.2 spread of the data, and zero point 0.2 basically the variance of the data. Virginica has the most variance. By variance, I mean the number of types of data we have. Like humans have a lot of variations. Like you can see there are Bengali people, there are Kashmiri people, then there are people from Bihar, and there is a lot of variation in the people. We can call it a variance, and we can capture the spread of the data. And in the similar way, you can see Setosa, there is a very less variation in the petal length. Petal length has very less variations. That's why the spread is only 0.03. And if you see in this Virginica, there is a little bit more spread. 0.3 spread. Here we have 0.2 spread. So now you got to know that the Setosa flowers, they will be looking more or less similar if you measure the petal length. There will be very less spread. So but Virginica, the spread is more. So for this Virginica flowers, so they will be having a lot of varieties, a lot of unique petal lengths. So that's why the spread is more. That's why we read this spread, so in order to understand the data. Now this Setosa you saw that it's clear, we can clearly distinguish it on the basis of petal length, because spread is very less, and these flowers are smaller in size, as you saw in the mean. Is clear how did we observe the data? So whenever you are making a graph, whenever you are doing some statistical tests, you must do one thing, that is you must write the observations. What is the observations? Because when you are doing the analysis of the data, you have to communicate this to some other people. So in order to do that, you must write the observations, whatever you observed from the data. This data looks like this, the mean is that, the spread is very less. I can write here in the observations, like I think the versicolor flowers will be really smaller. This is just by looking at it. I have never seen a versicolor flower in my life, but after analyzing the mean, the standard deviation, I can say Among the three flowers, the flowers which will be of the least size will have this, and will have very less variations, will have very less sort of variance, that will be the setosa flowers. And others, maybe the bigger flowers are virginica, and they'll have a lot of variation as well. Okay, never miss out the goal. The goal here is we are trying to classify the flower types into three classes: setosa, virginica, and versicolor. Make sure that you understand that first, and then that's why we are looking at these different properties. Is this clear? Unable to see your screens. Can somebody speak? Okay, nice. Let's move on to another statistical concept that's called as standard deviation. It's nothing, just we have to add a root, standard deviation. Now you saw that we squared this up. Every time you have this square over here, but the square sometimes bothers a lot of people because this gives a deviation, but it's a squared variation. But we want to get actually the absolute things, and we don't want the square. So what I can do is I can just put a root of variation, root of this variance. I'll get standard deviation. Okay, just to neutralize the effect of that squaring, I can put a square root to get the standard deviation. Again, it is a spread. It basically gives me the spread. It gives me nothing but the spread. But variance, actually we square them, and the spread over there that we got, it sometimes may be misleading, because if we have a value like 2, if we put 2 square, it will be 4. Okay, if we have 100 square, so it will be 10,000. So spread, the part of squaring, it amplifies the effect. But if you want to get the effect back, so you will just apply the square root to get the standard deviation. So again, the formula for the variance is take the data points, subtract the value of the mu, and then square it up for all the data points, sum these things up, and divide by total number of points. This is the variance. And now if I have to put the standard deviation, just put a square root over here. That is the standard deviation. The same thing here, it also measures basically the average variability. I can say it measures average variability. Similar thing, just to decrease that amplifying effect which the square does, the formula is basically the same. And sometimes some people, in order to just negate the effect, they say n minus 1, and there are some mathematical properties involved in that, but you just remember this n. Why this n minus 1? Because for example, sometimes there can be no points and we can divide it by 0, so it becomes like not defined and things like that. And people do handle it in different ways. I don't want to get into those mathematical debates to have n minus 1, and just have this n in your head. And you might see in the books sometimes they write n minus 1, n minus 1 instead of n, like sample number of points minus 1, to just deal with the mathematical property and have the coherent results. Okay, again we can compute this. To show you it on the coding window, I can just show you the standard deviation. We have what is called as STD, and you can also compute standard deviations by using the NumPy arrays. I have done all the computations by using pandas, but earlier I showed you that NumPy also, you can convert these things into NumPy arrays and directly apply that. Okay, so maybe I have mistyped something. I pasted some values over here. I don't know why, but still I'll see if I am able to. I was hoping to get an error here. Okay, now you saw that this is the standard deviation. Just having the square root over these things. This is the standard deviation of these flowers. 0.017, 0.46, and again you can clearly see that 0.17, the standard deviation of the petal length of setosa is less. The more spread, the more the standard deviation is more in the virginica flowers. As these standard deviation, mean, we discussed about mean, then discussed about variance, then discussed about standard deviation. All of these statistical properties, this gives a central tendency, and maybe these two things give us a spread of about data. But the problem they have, they were really sensitive to outliers, sensitive towards outliers. So what I mean by that is, if you just add an outlier, it'll whole skew the distribution in whole. Then we cannot say that this is the actual mean and it represents the standard tendency. Maybe tendency is something else, but just putting one outlier, it showed us the sum of the result. So in order to sort of mitigate those things, what do we do is we introduce some other concepts in the statistics so that they are not outlier sensitive. The first concept among them is called as median. median. Okay, so what median basically means, I'll show you that what median is. Median again shows you the central tendency. It shows you the again the central tendency, or maybe it gives a middle value as well. We can say. So how do we compute this? If you have data like this, x is equal to x1, x2, let's suppose x10. Let's take some real values. 1, 4, 6, 8, 9, 2, 12, 14. So these are the values that we have. If you want to compute the median, so what you do is you will arrange this in some order, either in ascending order or descending order. So what will be the ascending order? We'll put 1 first, then put 2 first, then 4, this 1 2 4, 1 2 4, then we have 6, then we have 8, 9, 12 and 14. So we ordered these things first in the ascending order. So when we order them, now the number of elements here is 1 2 3 4 5 6 7 8. So we have 8 elements. So you will take middle elements. So if the number of elements is even, so you will take two middle elements and you will perform the summation and compute the average of these two. 6 plus 8 is 14 by 2 is 7. So 7 is the median of value of these two things. If we had odd number of values, then the middle value is there. We had this 1 2 4 6 8 9 12. So now we have odd number of values. You just take the 6. The 6 is the median. Okay, what's the step? The step 1 is, step 1 we have arrange the data. Arrange data either in ascending order or descending order. Okay, what is the step 2? Step 2 is, if even number of elements are there, so then take two middle elements, take average of take average of two middle elements. Okay, but if the number of elements is odd, if odd, then what should we do? We should pick the middle one, middle element. Is this thing clear? Is the concept of median clear? How do we compute the median? Okay, the best thing here is it is robust. It is robust towards outliers. It performs the same thing as the mean does. Mean gives the central tendency, but it was having some problems with the outliers. So when we had outliers, then it was skewing it. It was sort of disturbing the mean. But here, the mean won't be disturbed. As you saw in here, for example, if we had another element, let's suppose 100. So if you put 100 over here, what will the mean now? The mean will be 8. So mean just got changed by 1. Even if we had this 100. Sorry, median. Median just got changed by 1. So 100, we got this median 8 because the number of elements turned out to be odd now. Then we'll take this 8. So median just got changed by 1 value. Even if you add 5000 in here, still the median will be similar. But with the mean will have a lot of impact on the outliers. Do you saw why is it robust towards this outliers? So how many of you understood this point? How is it robust to the outliers? Nice. Okay, so now I'll show you it in the code so that you also know that it is robust to these outliers. So going back to the coding window and showing you that. Here we compute the median by using the function medin, median. So you also can do it in the numpy. So now you see this. So median is 1.5 for this, 4.5 and 5.55. So if I just append one more values, let's suppose np dot, I'll append the values. Set was a petal length. Let's suppose I'll append value of 2000. Now you'll see nothing will change. You saw that still the median value is 1.5. Median did not, the outlier 2000 value did not impact the median. Okay, so is the concept of medians clear now? So can I move ahead? Nice. Now we'll understand what are called percentiles. Time is running so fast, I wanted to cover all of these things together. But hopefully we'll go slow, irrespective of how much time will it take, because I want you to have these concepts concrete in your head, because that way you learn a lot. It is not that I'll rush through these things and you'll get to know. At least you should know the breadth of the things. I don't want you to understand everything in depth, but at least have the enough breadth so that you can go into depth later on. But I don't want to do injustice with topics like that, which will be which will be the foundational building blocks for your career and the things like that. So we'll go into the percentiles and we'll learn about what percentiles mean. So it again is a statistical property, and it represents the percentage data falls into. What's the meaning of that? So if you have some data, what you will do is you will divide the data into 100 equal parts, Okay, that's why it's called percentile. Per means cent means 100, percentile means like per 100. That's why we call it a percentile. So simply, if you want to compute the percentile, let's suppose I have some data in which I have values like this, x1 comma x2 and so on till x100. Okay, if I take x50, the 50th percentile, this basically tells me how many values, like this 50th percentile tells me like there are 49 values or 49% of values less than this value. Let's suppose the value of the 50th percentile is 1.4. This basically means there are 49% of the values or 50% of the values which are less than or equal to 1.4. That's the meaning of percentile. Percentile basically gives, if somebody tells you what is the 99 percentile, so you can say what our value it is. Let's suppose this value is 5. So 99% of the data points that we have in our data are having the value less than 5. That's the meaning of percentile. And you might have even seen when the results come out for this NEET, JEE, GATE, they say that the guy has got a score of 99 percentile. That means he has got more marks than 99% of the students. Like at least 99% of the students have got less marks than him. Sometimes you might have seen 70 percentile. There's a difference between percentage and percentile. This is the percentile. 70th percentile means 70% of the students have got less marks than these. If somebody has, let's suppose, 450 marks, you might feel that he has 90% marks, but he might have 99 percentile. 99 percentile means that 99% of the students that were present with him, they got less marks than 450. But 90% basically means out of 500 he got 450. That's a 90%. Percentile means out of the whole population, out of the whole people that are present in an exam, how many people have got less or equal to marks than 450? Let's suppose that's 99 percentile. We call it a percentile, not a percentage. Is the difference between percentile and percentage clear? Can somebody speak?
Yes, sir.
So percentile basically gives us the idea about if you compute, so you will have 0th percentile till 100th percentile. So there can't be 101 percentile. So if you take x 60 percentile, so it will be telling you that if there is a particular value, let's suppose it's x60 is the value. So how many percent of points, like there will be 60% of the points which will have less than or equal to value like this. It is basically like CDF that we saw. Like on the similar lines, it's like that. And percentage basically is something else, but percentile is something else. Okay, so there are some famous percentiles called as 25th percentile, then 50th percentile, then 75th percentile. Okay, so they are called quartiles. Okay, they are called quartiles. This 25th percentile, 75th, this 50% and 70, like 100th quartile. So if somebody speaks about 25th percentile, this basically means 20 what is the value that is in the data which has the other values are like 25% of the values are less than that value. Okay, so 50th percentile basically is median. So what is median? Median basically says if we arrange the values in ascending or descending order, the middle value basically means on the left side there are 50% values, on the right hand side there are 50% values. So median basically is 50th percentile then, because median value tells us that 50% of the values are less than the median value. Okay, that's the 50th percentile. Median can be called as 50th percentile, and we call these as quartiles. Okay, and there is a concept called the interquartile range, IQR, interquartile range. If you subtract the value of 75th quartile and the 25th quartile, like 75th Q minus 25th quartile. This gives you the interquartile range, IQR. Okay, just remember these two things. Like, we started with the percentiles. Percentiles, basically we divide the data into 100 equal parts, then giving the value to all of these parts. And if somebody says me what is the 60th percentile, so I can say that the value we have at 60th percentile basically means that 60% of the points have less or equal to value than that. Okay, that's the concept of percentile. Then we have famous quartiles. Quartiles are 25, 50th, and 75th and 100th quartiles. So in the 50th quartile we call it median, because median is the middle value, and left hand side we have 50% values of that, and that's the definition of percentile basically. So 50th percentile is the median. Then we have something called as interquartile range. Interquartile range is if we subtract the 75th by 20, minus 25th quartile, then we get the interquartile range. Again, going back to the data to show you these concepts and to learn some and get some observations about data, and we'll see that. I think you understood the concept of these percentiles and quartiles. Okay, so here are these. So the first thing, I have these percentiles. So this is the 25th percentile, 50th percentile, 75th and 100 percentile. Like 1.4 petal length basically means in the setosa petal flower, 25% of the flowers have petal length of less than equal to 1.4. And similarly, the 50th percentile, or the median we call it. I have written the median over here as well. So the length is 1.5. That is 1.5 is the value that 50% of these setosa flowers have less than or equal to the petal length as 1.5. Again with the 75 similarly that. And 100 percentile means like every flower of setosa will have the petal length of less than or equal to 1.9. That's the 100th percentile. Is the concept of percentiles clear? Why are they important? Basically is if we want to get to know, if we suppose in the Amazon delivery, again taking that example. So if you know the distribution of the data, if you know that we have 95th quartile, and the value, again let's suppose we have 25th, and again we have 90 and 95th quartile. Let's suppose the expected delivery for most of the people, for 90% people, is 4 days. Okay, and for the 95%, let's suppose it's 8 days. Now you see that there is a huge shift of the 8 days. So they say that for very less people, for the last 10% of the people, we give like we give more than 8 days. So it's better we can just show the delivery order or delivery process or the shipment date to be just plus 4 days, because for almost 90% of the people, we are getting the delivery in 4 days. So it's better to show them the 4 days, because for the other like 95, it's a huge gap from here to here. So it's better to have the four, or even the video recommendations. If you have the percentile of the customer, so you saw the how much the people like this video. So what you do is, you know that 90% of people like that video in the percentile range. So and 10%, so you can recommend that video if you have the probability of 90, like at least this video has a particular metric, and on that metric 90% of the people like this video. So it's better to recommend the video to all the people. Okay, because we know that 90% of the people will like it, and there's a high chance and high probability that the people will click on that video. So we can use the concept of percentiles and concept of these quartiles. Is it clear? Can I move ahead? Can I move ahead? Somebody speak.
Yes, sir.
Okay, I think yes, we are on the right track. I think we can cover the whole things. Yes. So these are some statistical properties that we saw till now. We saw mean, then we saw variance, we saw standard deviation, then we saw median, then we saw percentiles, quartiles, interquartile range. Now we'll again go at a concept which is called as MAD. What is the meaning of MAD? MAD basically means median absolute deviation. Absolute deviation. Now you know that what is standard deviation. Standard deviation was if you put a square root on the variance. Again, there is nothing major here, so you will take each data point xi, then subtract it by mu, then take a mod of the values. Okay, you will take mod of these values and then summation over all the values divided by total number of points. So this is what is called as median absolute deviation. So here you are not applying the square itself, but in order to neutralize the effect of negative, you know how mod works. Mod of minus 1 is 1, and mod of 1 is also 1. So you're not amplifying the effect here. So you are in the first place not squaring this value. You are not taking that negatives into consideration, because this mod basically makes the negative value as positive value. Okay, that's called as the median absolute deviation, and we have also called as mean absolute deviation. In that mean absolute deviation, sorry, it should be median here, not mean. Let's suppose median is this median. So mean here is, if we put this mu, then it will be mean absolute deviation. But we'll usually take median absolute deviation because you know that the mean is, it is sensitive towards the outliers. So the best thing is to put the median over here if you want to. Again, it basically computes the spread of the data. But outliers, they don't impact it. So we saw mean, then its corresponding concept is median. We saw the standard deviation, its alternate concept is MAD, median absolute deviation, because these things are robust to outliers, and these things are sensitive to outliers. Sensitive to outliers. Okay, so that's how, like, we can compute this this mean deviation, mean absolute deviation, and median absolute deviation by again using the numpy or the pandas. So here I have computed that. So you can just see I have computed median absolute deviation for the setosa petal length is 0.14, basically the spread. Now here it ends the statistical properties that I wanted to talk to you about, and here we saw how to compute the standard tendency, how to see if there is spread, and how to get to know about the percentiles and quartiles and things like that. I hope that these statistical properties are clear. Now we'll do some other analysis by, everything here was till now was univariate analysis, univariate, because we are just taking one variable from one class to taking one variable and analyzing that. Now all these things were sort of summaries. It was summarizing things. It was sort of summaries giving what's the mean value, what's the standard deviation, and we were giving some numbers. Now we'd like to see some visual things, as we have seen that we want to see the data and we understand the visual impacts quite well. So we want to see visually all of these features. Like for example, if I want to see mean visually, so I should be able to do that. If I want to see this standard deviation, quartiles, and things like that visually, so how can I do that? As we have seen in Matplotlib, there are a lot of types of graphs. So now we'll at least cover 3-4 types of graph, so as to understand these concepts in a visual way, as we have seen that in a numeric way, in a textual format, or maybe in some summarizing way. Now I'll move on to and show you these things in a visual way by using the graphs. Okay, so are you ready with that? So are you ready to see the graphs?
Yes, sir.
Okay, the first graph that we'll see is, we'll understand what is called as box and whisker plots. I have shown you what histogram is, what these bar graphs are. Now I'll show you some other graphs. The first graph is box whisker plot. Whisker plot. Now you understood what is the meaning of the quartile, what is the meaning of the outlier, what is the minimum value, what is the maximum value. If I want to show you that visually, so in there what we have a plot like this. So we'll have a box like this, then it will have whiskers like this. Okay, then we'll have a line in between like this. This is how graph will look like. So what will it represent? This box basically represents, it represents the interquartile range. So it means this will be the 75th percentile, and this will be 25th percentile, and this line represents median. Okay, and sometimes, like, it depends on the implementation, this represent value represents minimum and this value represents maximum, and it varies from sort of implementation to implementation. Sometimes they use the quartile range like 1.5 multiplied by IQR to compute these values, whisker. Then might have triangles, and these are outliers. These things are outliers. This is how the graph will look, this whisker and box plot. So it will be having a box and the whiskers and the median line and the outliers. So here is the graph again. We'll have this box. So this box will represent basically interquartile range. Then we'll have this line, which will be the median, the 50th quartile. Then we'll have these whiskers, which will represent minimum or maximum value, or depending on the implementation. And then we'll have these dots sort of things, and it will consider the outliers. Everything that we saw before this was basically not in the visual format. Now we want to see everything visually, the min, max value, median, quartiles, and these outliers visually. So we can plot these things. And what is the, how to interpret these things? So that I have shown you clearly over here. This is the visual summary that we have seen basically. Going back to the coding to show you that. Oh, yes, I went to the coding window. Okay. So where are these graphs? So here are they. Yes. So I can use the matplotlib library to create these whisker and box plots, or we call them just box plots. So or box whisker plot. So I have a function box plot. So here I give the columns as petal length and the class. So I'll make basically I'm doing everything on the petal length for all the classes, all the three classes that we have. So the plots will be like this. So now you know that these dots, they're outliers. Now this is the median value. For the iris versicolor flowers, the median value is somewhere around 4. If you see this iris setosa, we have this median value around 1.4 or something like that. And then we have this interquartile range, like 50% of the points belong to this in this box. And the minimum value is right here, and the maximum value is, and this is an outlier. Okay, in the iris setosa we have other outliers as well. In the iris virginica, again you have this interquartile range first. So here green line is the median. So we have this box. So you just summarize all of the results, the mean, the percentiles and the quartiles and the minimum maximum and outliers in just one graph. You don't need to perform the statistical analysis numerically. You can just print this box and whisker plot, and you can get to know. Okay, now you clearly see that the iris virginica, they are higher in size. They're bigger in size. And you saw iris setosa, they're very smaller in size. And then you saw the box is a little bit smaller. You saw that the if you see the length of the box, it's smaller. So that it means the spread is very less. Okay, here the spread is more. Iris in virginica, the spread is more. If you see this, the median is higher, and here you can clearly see all those tests. And here we have some outliers. Here we have a lot of outliers in iris setosa. And in the seaborn, you can perform the same thing, but you will get a colorful thing of these box and whisker plots. This is the similar thing that we did by matplotlib, and you can do this by seaborn as well to compute these to basically print these box and whisker plots. Okay, is this clear? Is the concept of box and whisker plots clear? And how are we sort of summarizing everything that we studied so far, mean, median, everything in just one plot? Is that clear?
Yes, sir.
Yes, sir.
Nice. Now we'll go to other plots. So we'll go to other plot that's called as violin plot. After the box plot, we'll go to what is called as violin plot. Now you have these histograms. By histograms, you compute the CDF, and then from that you compute the PDF, and from the PDF you can compute CDF. And now I have these box whisker plots. I have histograms by the help of which I compute PDF, and I compute CDF from that. And then I have box and whisker plots by the help of which I can compute the statistical properties. This is one graph, and by this is the histograms. By the help of histograms, I can compute these things, and by the help of box and whisker, I can compute median. I can see percentiles, like visually basically. I can compute percentiles, interquartile range, then maybe maximum values, minimum values, outliers, everything. But what if I want to get the best of both the worlds? I want this PDF, CDF as well, and I want to get the box and whisker plot as well. For that, we have created what is called as violin plots. So violin plots, they basically combine the aspects of what is called as kernel density plots, KDE. It's called kernel density estimation. That's how we create the CDF and PDF. And they also sort of combine these things, the things that we have in box whisker plot or box plot that we have. Okay, so how do they look like? They look like this. So you will have a plot like this, and then it'll be like this. Then in between we have a box and a whisker. So here this is our box whisker plot, and here the outside, here it is PDF. This we can get by histograms, and this we can get by box whisker, and here we are combining both of these two things together. Okay, in order to show you this in the code, let's go back to the coding window and show you that. If I have created these graphs, let me see. Yes, here is the violin plot. We call them violin plots. In here, if you see, then we got this CDF. So just flip it the way. Just turn your head and look at it this way. So this is the CDF, and it's a symmetric figure over here. Then in between we have these box and whisker plots. So you can get the best of both worlds. You can get to visualize those CDFs as well, and you can get to visualize the box and whisker plots as well. This is what we call as violin plots. So it looks like violin, which is being like Like people do sing on that violin. It looks like, that's why it's called a violin plot. Is the concept of violin plots clear?
Yes, sir.
Nice. So now you saw how to use statistical properties and how to visually see those things now. How to visually see median, how to visually see quartiles. Now I think more or less we are done with the univariate analysis. So because we did what is called as univariate analysis, we just took one variable, uni, and one variable and analyzed that. Let's suppose here we were doing petal length because that was the most important feature we saw. Like petal length was the important feature based on which we saw that we can sort of figure out what's the class of the what's the class of these flowers. So that's why we did our whole analysis on uh, this petal length. But what we can do is we can also do what's called as bivariate analysis. Bivariate or multivariate analysis. If you see what was this bivariate pair plots, we saw that. So we saw how pair plots work. So we had one feature on one side and the feature on the other side. We saw this multivariate plots. We had these 3D scatter plots. Okay, we had in here we had 2D scatter plots. That was what we call as bivariate or multivariate analysis. So in there I would also like to show you one more thing. They're called as contour graphs. That will be the end of this analysis. Contour graphs. So how to basically see more than uh, one feature, more than two features at the same time. So if I go back to the coding window and I'll like to show you something first. So if you just write Gaussian distribution over here, Gaussian distribution, and if you go to the Wikipedia page, this is called sometimes normal distribution. I want to see the 3D of the normal. I think it is not here. Somewhere it should be. We call it multivariate Gaussian. Let's write multivariate. Multivariate Gaussian distribution. Right. Now we have it here. So if you see this graph over here, so you have sort of valleys and these crest and troughs on here. So there should be a better graph. And this one. So we have one axis, two axis, and three axis on here. So this is x-axis, then we have y and z, we have z-axis. Now you see that it looks like a mountain on the graph. So here we are analyzing three variables at the same time. I hope this graph is visible on your screen. So here we are analyzing the three things at the same time. So in order to visualize this thing, because all the time we cannot make things like this on the paper. So what we do is, because if you just draw a circle around these, if you draw a circle around this, all the values that will be on that circle will have the same value. So all these points which will be on the circle will have same values. So that's called as contour. So again, I like to show you here. So for example, if you have a graph like this 3D graph that we just saw, like this, it is spread across 3D. So if I just make a circle around this, every point that's on the circle will basically have the same value of the point at that time. Okay, at that point basically every point will have the same value at the surface of that circle. So you can plot these things like this. You can just now plot circles. So this is a circle, so we'll have a circle like this. So this basically corresponds to these values. So we'll have a circle like this, then we'll have some bigger circles, so we can have things like this. Okay, so these things are called contours. These are called contours. Contours basically mean the lines for which the value is similar in the 3D. So we had these 3D x, y, and z. So in that we had these 3D graph. If you want to analyze them, if you want to plot it on 2D, so we use contour plots. Okay, these circles, the value is same on the surface of circle. If you have a data point and it falls on here and something here, all these values will be similar. Okay, so we call it a contour plot. Just to show you that contour plots. So going back to the window, and I have created some example, I think, yes. So here we have this contour plot. So in here you have this x values, you have y value, then you have a z value as well. So in order to visualize this in a 2D plane, you just make these contour plots. Okay, we have this x-axis, y-axis, and this represents the z-axis, the values. They represent z-axis. So here the green basically means the less value. The farther you go in the circles,
Sir, screen is not visible.
sorry. So what I'm saying is, I'm saying we have generated the x values first, then generated the y values, and then generated the z values. So we have three values to analyze at the same time. So after I run this, after I plot this in this plot, I have a function called as contour in the matplotlib. So I gave x, y, and z, then gave the c map. So in here you can see that now we have circles. All these circles represent the same value. So this is the x value and this is the y value on the y-axis, and z-axis basically is the color. So you see the minus 1.0 is the least color that you have here. So here we have a lesser value. The more you go farther from the center, the values become higher and higher. So that's how you can analyze these things in the in like you can do multivariate analysis by using the contour plots, and you will get to know about this contour plots more when we're doing your assignments and things. So this sort of concludes our discussion on the explore data analysis. So there are some other tools that I would like to just name down so that if you see them somewhere and you at least know about these things. So the first thing is which you can use is called as factor analysis. You can also analyze the factors, factor analysis. So it basically explores the underlying factors which have some correlation and things. I don't want to go into the detail, but just know these. And there is something called as cluster analysis. Cluster analysis. Okay, then you can also do what is called as CCA, canonical correlation analysis. Canonical correlation analysis. So we also find correlations. We have not even seen this because I have just kept it when we will discuss about the stats and probability. That time we'll discuss about these. Then you have something called as discriminant analysis and other techniques like ANOVA and things like that. And there are a lot of techniques which we can again use to analyze the data more. But I think the techniques that we saw so far, they are more than sufficient to start with any sort of data. So here I will conclude this discussion on our explore data analysis. If somebody has question, maybe I'll take that. Otherwise, I'll stop the recording and I'll have some chat with you people.